Somewhere in our galaxy, right now, a dead star is spinning 700 times every second, and its magnetic field is so powerful it could strip the iron from your blood at a distance of 600 miles. That's not close to the strongest one. That's just where this list begins. Earth's magnetic field feels invisible to you, and yet it's the reason you're alive. It deflects streams of charged particles that would otherwise sandblast the atmosphere away, atom by atom, until nothing was left to breathe. Measured at the surface, it's about half a Gauss, a unit so small it barely registers on any instrument built for the extremes we're about to cover. A refrigerator magnet is stronger than the planet you're standing on. But that's the baseline, the calm floor beneath everything else on this list. Because the moment we leave Earth, the numbers stop making intuitive sense. Jupiter is next, and Jupiter cheats. It isn't a star. It isn't dead. It's just enormous. A ball of hydrogen and helium spinning fast enough to generate a magnetic field 20,000 times stronger than Earth's. That field stretches for millions of miles, so far that if you could see it from Earth, it would appear larger in the sky than the moon. Spacecraft that fly too close get bathed in radiation belts capable of frying electronics in hours. And yet Jupiter's magnetism is still gentle compared to what waits deeper in the catalog, because gas giants are amateurs next to what a dying star can do. The Sun comes next, and here's where the scale stops being about size and starts being about violence. Our star's magnetic field twists and knots as it spins, building up tension like a rope wound too tight, until it snaps in eruptions called solar flares. These flares can release more energy in minutes than humanity has produced in its entire existence. The field itself isn't much stronger than Jupiter's at the surface, but it moves, it lashes out. It reaches across 93 million miles of empty space to disturb satellites and power grids. Stars like ours are considered magnetically ordinary. What comes next is not ordinary at all. Sunspots are the visible scars of that magnetism, dark patches on the sun's surface where the field is thousands of times stronger than the surrounding plasma. Inside a single sunspot, the magnetic field can reach 3,000 Gauss, dense enough to suppress the boiling convection underneath and cool the surface by over 1,000 degrees. A sunspot the size of Earth can sit quietly for weeks, then unleash a burst of energy without warning. But even at its angriest, our star is a candle, next to what happens when a star like it finally dies. White dwarfs are what's left after a star like the Sun burns through its fuel and collapses. All that mass gets crushed into something roughly the size of Earth, and when a magnetic field gets compressed into a smaller space, it doesn't weaken, it concentrates. Some white dwarfs have been measured with magnetic fields exceeding 1 million Gauss, a number that sounds abstract until you picture what it would do to matter nearby. Atoms themselves would distort, their electron clouds stretched into thin cigar shapes instead of spheres, because the magnetic force would overpower the electric force holding them together. This is where physics starts to bend. But white dwarfs are still not where the true extremes live. To find those, you need a star that collapses even further, one that doesn't stop at Earth-sized, but keeps falling, until an entire sun's worth of mass is packed into a sphere no wider than a city. That object is called a neutron star, and it's here that magnetism stops behaving like anything you've ever encountered. Neutron stars form when a massive star runs out of fuel and its core implodes under its own gravity, crushing protons and electrons together into neutrons. The result is a ball roughly 12 miles across, so dense that a single teaspoon of it would weigh 1 billion tons. When a star that size collapses, its magnetic field collapses with it. And because that field can't simply disappear, it gets squeezed into a fraction of the space it used to occupy. A magnetic field that was already respectable in the parent star becomes almost inconceivable in the neutron star left behind. Typical neutron stars carry magnetic fields around 1,000,000,000,000 Gauss, 100 million times stronger than anything humans have ever generated in a laboratory. And still, this is only the entry point into the most magnetic class of objects known to exist, because some neutron stars don't stop at 1,000,000,000,000 Gauss. Some keep climbing into a category so extreme that scientists had to invent a new name just to describe them, and that name is magnetar. A magnetar is a neutron star with a magnetic field measured in the quadrillions of Gauss, roughly 1,000 times stronger than an ordinary neutron star, and roughly a quadrillion times stronger than the Earth's. At that strength, the field doesn't just distort atoms near the surface, it rewrites the geometry of space around the star itself. If a magnetar passed within 600 miles of you, the magnetic field alone would disrupt the electrical signals in your nervous system before you ever felt the gravity. No blade, no explosion, just an invisible field erasing the chemistry that keeps you alive. One of the most studied magnetars, SGR 1806-20, sits roughly 50,000 light-years away, and even from that unimaginable distance, a burst of energy it released in 2004 was powerful enough to briefly disturb Earth's upper atmosphere. Something that far away, reaching across the galaxy to touch us for a fraction of a second. If you've made it this far into the most magnetic objects in the universe, drop a like and subscribe, because the next entry doesn't just distort matter from a distance. It questions whether matter can survive being close to it at all. Magnetars are rare, and astronomers estimate there may be only a handful active in our galaxy at any given time, which raises an uncomfortable question. If one exists that we haven't found yet, drifting silently through the dark between stars, would we know it was there before it was already close enough to matter? Magnetars don't announce themselves. They don't shine brightly enough to stand out. They simply exist, radiating a field that could unravel your biology from hundreds of miles away, hidden in plain sight among billions of ordinary points of light. And this is where things become genuinely strange, because magnetars themselves may not be the ceiling. Some theoretical models suggest that under the right conditions, a collapsing star could form something even denser than a neutron star, a hypothetical quark star, where matter is crushed so far past the neutron stage that the neutrons themselves break apart into their most basic components. If such an object exists, and its magnetic field scaled the way physicists expect, the resulting field could exceed even a magnetar's by orders of magnitude, approaching numbers that stop being physically intuitive and start being purely mathematical. Nobody has confirmed one exists. Nobody may ever be able to, because an object that extreme might be nearly impossible to distinguish from an ordinary neutron star using the instruments we currently have. It's the kind of possibility that sits just outside the edge of what we can prove, a shape in the dark that our equations insist should be there. What all of this tells us is that magnetism, the same invisible force that holds a note to your refrigerator, is capable of scales that break the ordinary rules of matter entirely. It starts as something gentle enough to guide a compass needle. It ends as something that can dismantle the architecture of atoms from hundreds of miles away, generated by objects smaller than most cities, spinning in the dark corners of a galaxy that is mostly empty space and mostly silent. Earth's half a Gauss suddenly feels less like a fact and more like a mercy, a quiet exception in a universe built, in places, to erase anything that gets too close. If you're not ready to leave the extremes of the cosmos just yet, there's a full playlist waiting, where the black holes, the dying stars, and the forces that could unmake a planet are laid out one after another. Subscribe before the next magnetar wakes up, and we'll see you out there in the dark.